Hello everyone, myself Jaskirat Singh and I am currently studying in the 4th semester in a prestigious institute of Dr. B.R. Ambedkar National Institute of Technology Jalandhar. So basically we were given the assignments of subject heat and transfer, which we were asked to submit in either video format or document format. So I decided to do the following assignment in the video format. So I would be presenting my topic, which is transient heat conduction through large plane walls in the video format to Mr. Shashikant Yadav, who is our heat and transfer subject teacher. This course, Heat and Transfer, is a very interesting course. Basically, in this we study the forms of heat. What is heat? First of all, heat is a form of energy, and we study how it is transferred from one body to another, or how it works, its mechanism in this course. So, as I stated earlier, this assignment was given under the course of Heat and Transfer. I would like to present my sincere thanks to our HT professor Mr. Shashikant Yadav, who gave the opportunity to prepare the presentation on the topic transient heat conduction through large plane wall. I discovered many things while preparing this topic, and I deeply studied all the concepts, and all my doubts were cleared by Mr. our professor. And wherever I needed the help, I straightly asked him. He was very helpful throughout the assignment, and some sources I took from our book B.S. Datta, and some sources were taken from Wikipedia, but the plagiarism was not more than 15% as told by our professor. So in the upcoming slides, we will discuss the topic in brief. As discussed earlier, my topic was transient heat conduction through large plane walls. So first of all, I will explain my topic, the meaning of my topic. A transient stands for a very short duration of time. And as I mentioned earlier, heat is a form of energy. Basically, it is transferred through one object to another object by three modes, which are conduction, convection, and radiation. First of all, I would explain the conduction part. The conduction is process by which heat energy is transmitted through collisions between the neighboring atoms or molecules. Conduction occurs more readily in solids and liquids where the particles are closer together than in gases where the particles are further apart. Mode of transfer is required in conduction. Convection is the process of heat transfers by the bulk movement of the molecules within the fluid such as gases and liquid. The initial heat transfer between the object and the fluid takes place through conduction, but the bulk heat transfer happens due to the motion of the fluids. A medium is also required in convection. Radiation is the emission or transmission of energy in form of waves or particles through space or through a material medium. This includes electromagnetic radiation such as radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma radiation. A medium is not required in radiation. And through large plane walls are that walls in which the length is very large as compared to the width of the walls. By default, we take the width as 2L. So first of all, I will discuss the index of the project. First of all, we will discuss the objectives of our assignment. In the objective, we will discuss the variation of temperature, which is negligible, and temperature varies nearly uniform with time, making the simplified lumped system analysis applicable. I will discuss the lumped system in the further slides, and then we would obtain solutions for transient one-dimensional conduction problems in rectangular, cylindrical, and spherical geometries, which though is not my topic, but I would briefly, very shortly discuss about it and solve the transient conduction problems in large mediums. Construct solutions of multi-dimensional transient conduction problems using the product solution. Then we will discuss about the models of the transient conduction. There are three models. We will discuss in brief about the lumped system. What is lumped system? We will discuss the history of the Biot number, which was discovered by Jean Baptiste Biot in 1770, who was born in 1774 and died in 1862. and then we will discuss the various forms of transient heat conduction through large plane walls, its derivation, its exact solution, its boundary condition, graphical variations, and different studies. Some problems we will discuss about the transient heat conduction through large plane walls. Basically, we will discuss two problems. One is very easy and one is complex. And then in the end, we will discuss about the bibliography where I took the references from. So in this part, we will discuss about the objective. What is the objective of our assignment? This is very important part, because if we don't know about the objective, then what we can do? So we will access when the spatial variation of the temperature is negligible and the temperature varies nearly uniformly with time. This will discuss that the temperature varies nearly uniform with time, making the simplified lumped system analysis applicable. What is a lumped system I will discuss in the next slide, and then we will obtain an analytical solution of the transient one-dimensional conduction problems in rectangular, cylindrical, and spherical geometries using the method of separation variables, and understand why one term solution is usually reasonable approximation. Then we will solve the transient conduction problems in large mediums using a similarity variable and predict the variation of the temperature with time and distance from the exposed surface. This is a high level topic. We would not go in detail about this topic, but we will slightly discuss about this topic, and then we will construct solutions for multi-dimensional conduction problems using the product solution approach. And the models of the transient conduction, there are basically three models. We will discuss this lumped thermal capacity model, which is also known as lumped system, in detail, and the other two we will discuss briefly: the semi-infinite solid model and the finite sized model. The lumped system model is very important as we study about the transient heat conduction through large plane wall, because it is a type of lumped system, a complete lumped system. And the semi-infinite solid model and the finite sized model we will discuss in the last slides, and we will discuss the numericals of this part and one numerical of this part. So as I told earlier, when we talk about the transient conduction through large plane walls, we come through the concept lumped system analysis. This is very important topic. If we understand this, we can similarly we can understand the transient conduction through large plane walls. So what is a lumped system? I will explain it. Interior temperature of some bodies remain essentially uniform at all times during the heat transfer process. The temperature of such bodies can be taken to be the function of only time. It changes only with time, not with distance, not with length or any other dimension. Heat transfer analysis that utilizes the idealization is known as lumped system. A small copper ball can be modeled as the lump system. This is a ball. When we heat the ball, after some time, it reaches a steady state, uh, and then the temperature of such bodies, like a copper ball, is a function of time only, not the distance. We can see at all points its temperature is same, that is 70 degree at this point, 70 degree at this point, 70 degree at this point, 70 degree at this point. At all the points it is same at the surface, same at the bottom, same at the center. But whereas a case of roasted beef, it is not a lumped system. At the center its temperature is 40 degrees Celsius, at middle its temperature is 90 degree, and at the top surface its temperature is 110. Somewhere at the back there would be other temperature, and this way the temperature of such a body like a roast beef is not a function of only time, then its function of distance and any other dimension. So this is not a lumped system, this is a lumped system. When we discuss about the transient conduction through large plane wall, we consider that it is a lumped system, and then we do all the calculations required. So here we will do some of the calculations of the lumped system. As we know, in a lumped system, all the heat transferred through the body during a duration of time dt is used in the increase of the energy of the body. There is no wastage of energy. There is total 100% transfer of heat energy into the increase of the body during the temperature. So here we consider a lumped system, a solid body whose area is we take as AS, mass we take as M, volume we take as V, rho is the density, Ti is the initial temperature, and T is the temperature at which is a function of time at time T. H is we can take a constant, and so the Q rate of heat is equal to HAS bracket T infinity minus T at time T. This is a closed system. And T is infinity at T infinity, this is the temperature. So we will discuss it in detail. Heat transfer into the body during the time dt is equal to the increase in the energy of the body during dt. So this can be simplified as HAS bracket T infinity minus T in time dt is equal to mCp dt, which is rise in the energy. This part is the energy. So m can be written as rho v, m is mass, rho is density, v is volume, and d capital T can be written as d, which is change in the temperature, T minus T infinity. So putting the values, we get it d T minus T infinity upon T minus T infinity is equal to minus of HAS upon rho v Cp dt. So we can integrate this equation by putting t is equal to Ti at t is equal to small t is equal to 0, and t is equal to t, which is a function of t at time is equal to t. So we get this basic formula, which can be obtained by integrating this from this values, this limits. We get ln t small bracket small t minus t infinity upon T initial minus T infinity is equal to minus of HAS upon rho VCP T. So this can be written as log when go this side, this becomes the exponential term T bracket T minus T infinity upon T initial minus T infinity is equal to exponential of minus BT, where B is equal to this part HAS rho VCP. We simplified B as this, and this is called time constant, and its units are 1 by S. So we get these equations, and we have to remember these equations. So here we plotted a graph versus T, temperature versus time. T is function of only time. From graph we can confirm it. So this equations enables us to determine the temperature T at times small t of a body at time t, or alternatively the time t required for the temperature to reach the specified value, which means vice versa, which means the same thing. The temperature of body approaches the ambient temperature T exponentially. This temperature, the temperature of the body changes rapidly at the beginning but rather slowly later on. A large value of B indicates that the body approaches the environment temperature in short time, which means if the B value, which is this value, if this is large, then the time taken is small. This time taken is small. If the B, we can see that B3 is greater than B2, which is greater than B1. If we see B3 reaches this T infinity temperature in less time, B2 in more time, and B1, which is smallest, in the maximum number of time. The temperature of lump system approaches the environment temperature as it gets larger. B3 is greater than B2 if, and then B1, the slope is greater. B3 slope is greater, B2 slope is less than B3, and B1 is the least. All about this slide. So in this slide we will discuss about the rate of convection of heat, the total amount of heat transfer, and the maximum heat transfer between the body and its surrounding. This is a very similar equation which we studied in the lumped system analysis, where we studied about the geometry and the transfer of heat through the lumped system. This is the same equation we studied there, but here is a dot which represents something else. I will tell it later on. Q, which is a function of time, is equal to HAS capital T function of time minus T infinity. This is the rate of convection of heat transfer between the body and its environment at time T. Now we will discuss the total amount of heat transfer between the body and the surrounding medium over the time interval t is equal to 0 to t. So q is equal to mcp capital T, which is a function of time only, minus T initial. The units are kilojoule. And the Q maximum is equal to mCp. Here we put the value at T infinity and minus T initial. These equations are same, only we replaced the function of time with infinity, the temperature reached by the body at infinity. This is the maximum heat transfer between the body and surrounding. Here a lumped system is shown. Here is also a lumped system is shown, which is at initially at temperature Ti, and this to reach the temperature at T infinity, the temperature at time infinity, and the time taken is T infinity to reach the temperature T initial to T infinity. So the maximum heat transfer can be written as mCp T initial minus T infinity, which is Q max. Heat transfer to or from the body reaches the maximum value when the body reaches the environment temperature. So now we will discuss the criteria for the lumped system. What criteria needs to be satisfied to make a lumped system? So a lumped system is basically a solid body. Mostly we see a solid bodies as a lumped system, in which the heat is transferred through conduction, and from the environment the heat is transferred through the convection. So here we take small h, the temperature is T infinity, and the basic means the terms which used in this chapter are characteristic length, which is denoted by LC, which formula is equal to V upon AS, and the most important things, the Biot number. What is Biot number? I will tell about the Biot number. The Biot number is dimensionless quantity used in the heat transfer calculation. It is named after the 18th century French physicist Jean Biot, who was born in 1774 and given the simple index of the ratio. Biot number can be anything between less than 1 is equal to 1 or greater than 1, but for the lumped system analysis applicable only if the Biot number is less than 0.1. When B, which is denoted for Biot number, is less than 0.1, the temperature within the body relative to the surroundings, that is T minus T infinity, remain within the 5% of each other. This is very important, so I added this in this slide. So but what is Biot number? Biot number is a heat convection upon heat conduction. This is a dimensionless quantity because both the units cancel each other. Heat convection from the surroundings to the heat conduction within the body. So this can be written as B is equal to H upon K upon LC, and rate of change of T upon T, which can be written as convection at the surface of the body and conduction within the body. So BI is equal to LC upon K is equal to 1 upon H, the conduction resistance within the body and the convection resistance at the surface of the body. So now we will discuss the from where the Biot number came into existence. This is the history. Though we science students are not interested in the history, but it is some people are interested to know the history also. So this Biot number was named after the French physicist who was born in 1774 and died in 1862, and was a French physicist, astronomer and mathematician born in Paris, France. Although younger, Biot worked on the analysis of heat conduction even earlier than Fourier did. Fourier was also a famous scientist. We study about Fourier series and all other in mathematics, did in 1802 or 1803. This shows that the Jean Biot discovered it before Fourier and attempted unsuccessfully to deal with the problem of incorporating external convection effects in the heat conduction analysis. Fourier read Biot's work. Fourier considered Biot as his guru, and by 1807 had determined for himself how to solve the elusive problems. In 1804, Biot accompanied Gay-Lussac we study in chemistry, on the first balloon ascent undertaken for the scientific purposes. In 1820, with Felix Savart, he discovered the law known as Biot's and Savart law. This we discussed in physics in class 12th. Biot's and Savart law, for which we study to find out the current in large uh, in long rods and other things. He was especially interested in questions relating to the polarization of light, and for the achievements in the field he was awarded the Rumford Medal of the Royal Society in 1840. The dimensionless Biot number used the transient heat transfer calculation is named after him. I mentioned about Biot-Savitz's law in this. This is very similar to the Coulomb's law in electrostatics. The law is applicable to small conductors to carry current. This law is applicable to for only symmetrical current distribution. So Biot was a very good scientist. We should admire him, I say. Now we can see some numerical part. So here we consider a spherical copper ball whose K is equal to 401 W per meter per Celsius, D is diameter is 12 centimeter and H is 15 W per meter square per Celsius. Small bodies with higher thermal conductivities and low convection coefficients are most likely to satisfy the criterion of the lumped system analysis. So LC can be calculated V upon AS is equal to the volume 1 by 6 pi d cube and the area pi d square comes out cancellation 1 by 6d. So upon calculating we get 0.02, and by its number we get H upon LC by K, which is equal to 15 into 0.02 upon 401 is equal to 0.00075. For lumped system, I told before, is always less than 0.1. When the convection coefficient H is high and K is low, the large temperature difference occur between the inner and the outer regions of large solid. This part. This cannot be said as a lumped system. Analogy between the heat transfer to a solid and passenger traffic to an island. In this diagram it is shown very nicely. It is an island. Here is the boat. The heat is transferred through the fluid by convection at the surface, but in the inner within the island by buses through conduction. This is an analogy. So now we will discuss the transient heat conduction in large plane walls, long cylinders and spheres with spatial effects. So my topic is restricted to large plane walls, but we will slightly discuss about this also, long cylinders and sphere. So we will consider the variation of temperature with time and position in one dimension only. Problems such as associated with large planes. So we will discuss the transfer of heat or the temperature in one dimension, this dimension only, not in this dimension. We don't consider this direction because the width is very small as compared to length, so the heat is transferred only in this direction, not in this direction. So basically I will tell all the assumptions we took. So we consider a plane wall of thickness 2L. The length is L from the center, so total length is 2L. A long cylinder of radius cylinder we will discuss later on. At time t is equal to 0, each geometry is placed in large medium that is constant temperature at T infinity and is kept in that medium for time t is greater than 0. Heat transfer take place between these bodies and the environment by the convection with uniform and constant heat transfer coefficient H. The plane wall is symmetrical about its center, that is equal to R is equal to 0. The cylinder is symmetrical about its center line R is equal to 0, and the sphere is symmetrical about its center point R is equal to 0. We neglect the radiation heat transfer between those bodies and the surrounding surfaces, or the incorporate radiation effect into the convection heat transfer coefficient. The variation of temperature profile with time in the plane wall is illustrated in the figure. When the wall is first exposed to the surrounding medium at T infinity, which is greater than T initial, at T is equal to 0, the entire wall is at the initial temperature Ti, but the wall temperature at and the near the surface starts to drop as the result of heat transfer from the wall to the surroundings medium. This creates a temperature gradient. Gradient means difference in the wall and initiates heat conduction from the inner parts of the wall to the outer surfaces. Note the temperature at the center of the wall remains at Ti until T is equal to T2, and that temperature profile within the wall remains symmetric at all the times about the center plane. The temperature profile gets flatter and flatter as the time passes as the result of heat transfer. This is T2 and this is Ti, this is T3, small t3. The wall reaches thermal equilibrium with its surrounding. At that point the heat transfer stops, since then there is no longer a heat temperature difference. Similar discussions can be made with the long cylinder or sphere. So I discussed all the theory part here. So now we will move to the next slide and we will obtain the exact solutions and the formulas of this large conduction plane walls. So non-dimensional, one-dimensional transient conduction, I discuss it is one-dimensional. Heat transfer is only in one direction, not in this direction. The total length is 2L. This comes out to be small l because it is symmetric about its center. The outside temperature is T infinity and the initial temperature at the center is Ti. So we derive the following equations. Differential equation is equal to del square T upon del x2, which comes out to 1 by alpha del T upon del small t. Boundary conditions, when we put the following boundary, uh, which is equal to 0 comma t upon del x is equal to 0 and minus k upon minus k del t, and which is a function of length comma time upon del x is equal to h bracket capital T's, which is a function of L comma T minus T infinity. So initial conditions we took as T x comma 0 is equal to Ti. So alpha is equal to K upon PCP. X is equal to small x upon L. Theta x, which is a function of x and t, is equal to capital T function of x comma t minus T infinity upon Ti minus T infinity. So this comes out to be del square theta upon del x square is equal to L square upon alpha del theta upon del t, and del theta bracket 1 comma t upon del x is equal to hl upon k theta 1 comma t. Dimensionless differential equations. So these three equations we will remember. Del square theta upon del x2 is equal to del theta upon del tau. Dimensionless del theta bracket 0 comma tau upon del x is equal to 0 and del theta bracket 1 comma tau upon del x is equal to minus bi by its number theta 1 comma tau. Dimensionless initial conditions theta comma theta, which is a function of x comma 0 is equal to 1. Dimensionless temperature theta x comma tau is equal to T, which is a function of x comma t minus T initial upon T infinity minus Ti. The dimensionless distance from the center is equal to capital X is equal to small x upon L. Bytes number we discussed earlier, which is also a dimensionless heat transfer coefficient. Bytes number, which the scientist Jean Byte discovered, is equal to h upon L by k, and dimensionless time, which is denoted by this symbol tau, is equal to alpha t upon L square, which is also known as Fourier number because Fourier scientist also discovered with Byte. And this reduces the number independent variable. That's why it is non-dimensional. Reduces the number variable. It reduces the number independent variables to one dimension transient conduction problems from 8 to 3, offering great convenience in the presentation of results. So that's why most of the units are dimensionless. So original heat conduction problem, del square theta is equal to del x2 is equal to 1 by alpha t del t upon del small t. Conditions tx comma 0 ti. So these are the conditions we need to take care while for taking the numericals into action. Now we will discuss the exact solution of one-dimensional transient conduction problem. This is very complex topic, so we need to uh, study it very deeply and very slowly. So we consider theta as a function of capital X comma tau is equal to function of x and g of tau. So 1 by f is equal to d2 f upon dx square is equal to 1 by g dg upon d tau, and d2 f upon dx2 plus lambda square f is equal to 0, and dg upon dt plus lambda square g is equal to 0. This part is related to maths in linear equation chapter. So f is equal to c1 cos lambda x plus c2 sin lambda x, and g is equal to c3 e to the power minus lambda square tau. Theta is equal to fg is equal to c3 e to the power minus lambda square tau, which comes out to be in bracket c1 cos lambda x plus c2 sin lambda x is equal to e to the power minus lambda square tau comma a cos lambda x plus b sin lambda x. A is equal to c1 c3 and b is equal to c2 c3. So now lambda theta, which is a function of 0 comma tau upon lambda x is equal to 0, which approaches minus e to the power minus lambda square tau a lambda sin 0 plus b lambda cos 0 when we put the values of lambda x is equal to 0. So b is equal to 0 and theta is equal to a e to the power minus lambda square tau cos lambda x. So lambda theta, which is a function of 1 and tau, is equal to upon lambda x is equal to minus bi theta bracket 1 minus tau comes out to be minus ae to the power minus lambda square t lambda sin lambda is equal to minus bi a e to the power lambda square t cos lambda, which approaches on cancellation of this, it becomes a sine upon cos becomes tan lambda, which is equal to the Biot number. So Biot number can be written as lambda n tan lambda n. So this is the generalized formula. Theta is equal to summation of n is equal to 1 to infinity a n e to the power minus lambda square n to the power tau cos or function of lambda n x, and theta, which is a function of x0 is equal to 1, can be written as 1 is equal to summation of n1 to infinity a n cos lambda n x. So on integrating we get this formula: integration of 0 to 1 cos lambda n x dx a n 0 to 1 cos square lambda n x dx. So a n comes out to be 4 sin lambda n 2 lambda n plus sine 2 lambda n. So we don't need to remember this part, we only need to remember this part. So here a summary table is shown, summary of solution of one-dimensional transient conduction plane wall, which we solved in the previous slide. The calculation part is not in our syllabus, we only need to remember this part, and the calculation is required in the higher levels, in PhD level or MTech level. So similarly we can solve for a cylinder or sphere, but it's not mentioned in my topic to discuss about this, but I have added this in this slide, so I will once go through this. So plane wall become theta is equal to summation of n is equal to 1 to infinity 4 sin lambda n upon 2 lambda n plus sine 2 lambda n e to the power minus lambda square t cos lambda n x by l. So roots are 1 n tan 1 n 5 bi. Similar for cylinder we can discuss, and for sphere this chart can be very helpful for solving the numerical part. So same theta is equal to a n e to the power minus lambda square n tau cos lambda n x. A n is equal to, which we solved, 4 sin lambda n upon 2 lambda n plus sine 2 lambda n, where lambda n tan alpha is equal to Byte's number for different values. Byte number 5, x1 and t0 table is plotted. You all can see the values of the table. The analytical solution of the transient conduction problem typically involve the infinite series, and thus the evaluation of infinite number of terms determine the temperature at the specific. This is common, all the 12 students can solve this, because infinite series we have learned in arithmetical progression and geometrical progression chapter. The term in the series solution of the transient conduction problem decline rapidly as n, and thus lambda n increases because of the exponential decay function with the exponent of minus lambda and tau. So here we have discussed the approximation, analytic and graphical solution. The terms in the series solution converge rapidly with increasing time, and or tau is greater than 0.2, keeping the first term neglecting all the remaining terms in the series results in the error under %2. Solution with one term approximation. Plane wall, theta wall is equal to t of xt minus t infinity upon ti minus t infinity is equal to ai e to the power minus lambda square tau cos lambda 1 x by l, where tau is greater than 0.2. Similarly for cylinder, this equation, and for sphere this equation come out, and when we put center of the plane wall x is equal to 0, we get theta 0 volt t 0 minus t infinity upon ti minus t infinity. A is equal to a1 e to the power minus lambda square t. This is important. This can be used in numerical. Similarly, this can be also used in numerical, but this is not my part. Here is a table coefficient used in the one-term approximation solution of transient dimensional heat conduction plane wall cylinder and spheres. Byte number HL by K for plane wall of thickness 2L, and byte number H R for cylinder of sphere. Here byte number, different byte number for plane walls lambda 1 AI. We have plotted different values of byte number for different lambda 1 for A1. Similarly for cylinder, different lambda 1 we get different A1. For sphere, different lambda 1 we get A1. The zeroth and the first order of the Bessel function of the first kind. Eta, for different values of eta we get different value of J0 and Ji. Here is a graph of mid-plane temperature. Theta naught is equal to T naught minus T infinity upon Ti minus T infinity. The graph is plotted. It is a very complex graph, you can see, and tau is equal to alpha T upon L square. This is the plane wall we have discussed before. The transient temperature and the heat transfer chart. This is called Hessler and Grauber chart for the plane wall thickness of 2L initially at the uniform temperature Ti, subjected to the convection from the both sides to an environment temperature T infinity with convection coefficient of H. So now we discuss about the temperature distribution. Again we have drawn a transient conducting wall. Temperature T infinity H is T infinity H. The distance from the center to the boundary is L. Total distance is 2L. So theta by theta naught we have known T minus T infinity upon T naught minus T infinity. When we plot the graph, we get this. This is kind of a logarithmic function, reverse logarithmic function. Different value of x by L, we get 0 by 2, 0 0.4, 0 0.6, 0 0.8, 0 0.91, where 1 by Bi is equal to K by HL. So this is the temperature distribution graph. Similarly, we get heat transfer graph. The graph is plotted. We all can see the scale is very important. 10 raised to power minus 5, 10 raised to power minus 3, 10 raised to power minus 2, and here we have plotted 0.1, 0.2, Q upon Q max. Byte's number is Bi is equal to HL upon K, and this is the graph of heat transfer. So now the dimensionless temperature anywhere in the plate, cylinder or sphere are related to the temperature by the formula theta upon theta wall upon theta 0 comma wall cos, which is a function of lambda 1 upon x by L. This was for large plane walls. This for cylinder, theta cylinder upon theta 0 comma cylinder J naught lambda 1 r upon r naught, and this for sphere, which is equal to sine of lambda 1 r upon r naught, lambda 1 r upon r naught. This is diagram for finite convection coefficient, and this is for infinite coefficient. The specified surface temperature corresponds to the case of the convection to the environment T infinity with a convection coefficient h that infinite. We will revise all the formulas. Q max is equal to mCp T infinity minus Ti is equal to rho Vcp T infinity minus Ti for plane wall. Q upon Q max wall is equal to 1 minus theta for condition 0 comma wall sine lambda 1 upon lambda 1 cylinder. Q upon Q max cylinder is equal to 1 minus 2 theta 0 comma cylinder j lambda 1 upon lambda 1 sphere. We can see here. So we derive a generalized formula. Q upon Q max is equal to integration from V PCP T x comma T minus Ti upon PCP T infinity minus TIV dV 1 upon V integration from V 1 minus theta dV. So it comes out to be Q is equal to PCP T, which is a function of x comma T minus Ti dV. So here is the diagram shown. Maximum heat transfer. This is a body, this is a body. T I T infinity, at T infinity Q naught max is reached maximum heat transfer, and Barrett's number Bi, which you know the formula, and Grober's chart we have all discussed before. The fraction of total heat transfer Q upon Q max up to specified time is determined using the Grober's chart. Now we will discuss the physical significance of the Fourier number. Tau is equal to alpha T upon L2 minus is equal to KL square 1 by L delta T upon PCP L cube upon T delta T. The rate at which the heat is conducted across the L of the body of volume L cube upon the rate at which the heat is stored in the body of volume L cube. The Fourier number is the measure of heat conducted through the body relative to the heat stored. Here is a cubical body shown. Heat is conducted in this direction, heat is stored in this direction. Q dot stored, Q dot conducted, L side, L side, L side. The Fourier number is tau is equal to alpha T upon L square is equal to heat conducted upon heat stored. The large value of Fourier number indicates the faster propagation of heat. It only indicates the faster propagation of heat. Fourier number at time t can be viewed as the ratio of heat conducted to the rate of the heat stored at that time. We will discuss about the transient heat conduction in the semi-infinite solids. The semi-infinite solid is an idealized body that has a single plane surface and extends to the infinity direction. This is a semi-infinite body. Plane surface, center at 0, this direction x, this infinity, temperature infinity h. A thick wall can be modeled as semi-infinite medium if we all are interested in the variation of temperature in the region near of the surface and the other surface is too far to have an impact on the region of the interest during the time of observation. For shorter period of time, most of the body can be modeled as the semi-infinite solid since the heat does not have sufficient time to penetrate deep into the body. The Earth can also be considered as a semi-infinite medium in determining the variation of the temperature near the surface. So this is a semi-infinite body here, you can see. We will discuss the analytical solution for the case at the constant temperature for a surface. Differential equation is del 2t upon del x square is equal to 1 by alpha del t by small del t. Boundary condition t for 0 comma small t is equal to ts and tx approaches infinity comma t to ti. Initial conditions are t x comma 0 at ti. Similarly, variable eta is equal to x upon under root of 4 alpha t. Similarly, this formula at boundary conditions, this air function of eta is equal to 2 upon under root of pi 0 to r 0 to eta e to the power minus u du air function. Transformation of variables in the derivatives of the heat conduction equation by the use of chain rule. Chain rule is used to derive this. Here is the derivation, you can see. So now we will discuss one simple numerical. In the question is, in the production facility, large glass plates of 4 centimeter thickness they are initially at uniform temperature of 20 degrees Celsius. This is a brass plate initially at 20 degrees Celsius are heated by passing them through the oven is maintained at 500 Celsius. So initial Ti is equal to 20 degrees Celsius and T infinity is equal to 500 degrees Celsius. The plate remains in an oven for a period of 7 minutes. Time is 7 minutes. Taking the combined convection and the radiation heat transfer coefficient to be H is equal to 120 Webers per meter square per Celsius, determine the surface temperature of the plates when they come out of the oven. So this is a plate. The temperature initial is 20 degrees Celsius. T infinity after 7 minutes is 500 degrees Celsius. This is placed in oven. H is given to be 120 Webers per meter square per Celsius. So 2L is equal to length 20 degree 4 centimeter, which comes out with. So we take assumptions. Heat conduction in the plate is one dimensional. The thermal properties of the plate and the heat transfer coefficient are constant. The Fourier number tau is greater than 0.2, so that the one term approximation solutions are applicable. The properties of the brass at the room temperature are K is equal to 110 Weber per meter per degree Celsius, and all the other conditions are given here, alpha value, Cp value. So analysis. The temperature at specified location at the given time can be determined by the Hausler charts, noting that are half thickness of the plate L is equal to 0.02 meter from figure. So Bytes number formula 1 by Bi is equal to K upon HL is equal to, by putting the values we have to take special care of the units that all are in the same SI units. So putting the value, this comes out to be 45.08, and tau comes out to be, by putting formula alpha T upon L square, it comes out to be 35.6. This is also calculated. All the values are noted, or we all can see that all these are dimensionless quantities. This was done by Bytes to reduce the uh, dependent of one variable to another, and we can all draw easy result from this formula. So T minus T infinity upon T I minus T infinity, this comes out to be 0.455. So T temperature T infinity plus 0.455 T I minus T infinity is equal to 500 degrees Celsius plus 0.455. 20 minus 500, this comes out to, this is the required answer. So here comes the summary of the topic. I completed the topic transient heat conduction through large plane wall, which is a very complex topic. I studied thoroughly the topics, and I want to express my sincere thanks to my professor who helped me in providing his guidance wherever I needed it. So the bibliography, the transient heat conduction was a very interesting topic, and I discovered good knowledge through the topic, and I took the books reference from the books BK Datta, and some topics I studied from the Wikipedia. So this was all from me, myself, Jaskira Singh, roll number 19112040, signing off before you. Thank you for listening to my PPT. So stay home, stay safe until we all get vaccinated and live the happy life again. I hope so. College reopens and we all meet each other and discuss all the topics in the classroom.